So in this video, we're going to talk about garbage in, garbage out, which is a really important concept in machine learning, and it's really important a way to diagnose whether a machine learning algorithm is doing well or not. You can call BS on machine learning algorithms. So the first important thing that I want to say is that this video owes a huge debt to this amazing book and course and website, Calling BS by Bergstrom and West. I've got my copy here. It's a fantastic book. You should check it out. I'm really modeled this video on the stuff that they say in that book and in their videos. So here's a picture for how big data machine learning models work. This is the kind of concept that we get about big data models from popular media. You have lots and lots of data, you chuck it into some algorithm, and then you get some output at the end of that. Now, machine learning is a little bit more complicated than that. In machine learning, you actually don't start off with an algorithm at all. You don't have anything. You might have the idea that you want to use a neural network or something to make some prediction, but you start off not having an algorithm at all. You have to train the model based on data. So you don't have an algorithm to make any predictions until you actually input some training data into the algorithm. And once you use some training data, so it might be some data with some data and with some labels. You can use that to train something like a neural network, like a piece of deep learning or some other algorithm, and you end up with a trained algorithm based on data. Once you have that trained algorithm, what do you do then? Well, if you actually want to make some predictions, if you actually want to use the thing, then you need to pump in some real data. And once you pump real data into your into your algorithm, that's when you get outputs. So the situation for modern machine learning is that we only have an algorithm. We only have these models to do things by having training data, right? And using the training data to train an algorithm. And then pumping real data through that same algorithm and getting some outputs. And so we hope that these two things match up and give us useful results. So there's a whole industry on how to train these algorithms and whole data sets that machine learners use to be able to do things. So here's the classic sort of problem that you would have in machine learning. You have some training data on things like handwritten digits. So you have a data set which has got hand drawings of lots of numbers. You would use that in conjunction with the labels on these numbers. So we've got a 5, a 0, a 4, a 1, a 9, a 2, etc., etc. So you have these encoded, and then you train your black box algorithm to try and predict these labels from the input data. So that's an example of some good training data and of a classic data set that you would train a machine learning algorithm on. And then you would chuck some real data into your trained model. So it might be some more difficult data. So here are some numbers that look like, that we might be able to tell what they are, but some of them are a bit sketchy. Like this third one along here, is that a 0 or is that a 6? Is this one over here? Is that a 1 or is that a 7? These, we've got 6s or 5s down here. So, it becomes a bit more difficult. And so this is, there's a whole world of machine learning that is about taking data sets like these, training algorithms, and then seeing how well they work on new unseen data. And so here's the point of what we want to get to here. There's an important concept in understanding these models called garbage in, garbage out, right? So if I happen to take my training data, if the training data was wrong, if the images on the left didn't match up correctly to labels on the right, then my algorithm would learn sort of garbage relationships between data and labels, and then it would not generalize very well. It wouldn't be able to perform very well in detecting digits in new real data. So that's particularly important when you get to real world data, which can be a bit more messy. So the idea in garbage in, garbage out is if the model is trained on bad data, then it will produce bad outputs. And so this is actually important. This is a way that you can diagnose whether an algorithm is doing a good job or not. You can tell whether it's doing a good job by looking at the training data, looking at the inputs, and looking at the outputs as well. And you can sometimes diagnose what's going wrong based on that. So here's an example of this. Here's a real data science study that somebody did. This was in an XKCD comic where they looked at the rates at which different days of the years with different dates during the year got represented in Google Books. So Google Books is a huge corpus of text from books from throughout history. So the author looked at translations of books since 2000, and you can see that the first of each month gets talked about a lot. Each number here is sized based on the frequency at which it comes up. The 4th of July comes up a lot. September the 11th since 2000 comes up a lot. New Year's Eve comes up a lot. And there are all these other interesting patterns here. So data scientists got excited about this, and they went and looked for some more patterns in this. And they noticed something interesting. If you look really closely at this calendar, if forgetting about September, if you look at the 11th of each other month, so the 11th of July here, you can see is relatively small. The 11th of June is relatively small. And actually, it looks like, if you squint closely, it looks like the 11th is kind of underrepresented here. So for some reason, people are not talking about the 11th of each month in these books as much as we might expect. You can count this more formally. People did this. So they looked at the frequency, made a histogram of how frequently each day of the month came up. And you can see that the first of each month is relatively frequent in the books, but the 11th of the month is an outlier. So why is that? Why do people not talk about the 11th of the month as much as other dates? You can look at this over time as well. Here's a similar sort of plot, and you see that the 11th of the month has been decaying over time. It's being talked less and less over time, going down. Why is that? Right. So that's a mystery. Right. There's a whole whole bunch of data scientists, a whole bunch of people wondered about this and started to think: is there something cultural going on here? What's the story with why the 11th of each month is not being talked about in books, and why is it going down over time? So at this point, I want you to pause the video, have a quick think about this. Have a think about whether you believe this or not, what you think is going on here. Pause the video, have a think, and then come back and we'll talk about what's happening here. Okay, so if you didn't pause the video, you should have, but that's okay. Let's have a think. Do we believe this? Why is the 11th of the month have this strange pattern? Well, it turns out it's related to this handwriting recognition example I just talked about before. Think about, what does 11 look like? Well, it looks like 2 strokes, right? So turns out what actually happens is if you look at, if you count up the instance of 11, if you count up the instances of nth, and if you count up the instances of things like xx, what's actually going on here is the 11s look like L's, or they can be confused as an N sometimes. So actually the machine learning algorithm, the character recognition was not working here in this corpus. And if you add up the 11s that have been mistaken as N's or as other characters, then you get something that's in the bulk of the distribution. So we should call BS on this strange finding that the 11th of each month is for some mystical reason underrepresented in book entries, and think about what are the inputs and the outputs to this machine learning model, the machine learning that's going on here and doing the handwriting recognition, what's going on with the inputs, how could they be mistaken, and we should be a bit skeptical about these claims that are being made. So, here's another example of this. At the time of writing, the time of creating this presentation, ChatGPT is the hot piece of machine learning, and you can ask ChatGPT questions, and it will give you answers. So, as it turns out, it's easy to fool ChatGPT. So you ask it something like, what's 2 to the power of 8/3? And it gives me some very convincing mathematics that it rearranges here using a particular rule, and then it tells me 2 to the 8/3 is equal to 4. You can do the same thing. You can give it in Python notation, and we'll say, oh, that's Python, that's exponentiation, so we can do power of 2 to the 8/3, and that comes out to be 4. Of course, that's not true. 2 to the 2 is 4, of course, and 8/3 is not equal to 2. So this is 6 and a bit. You can even put the code into Python, and it comes out like that. So why is this? Well, I mean, ChatGPT is truly a black box, right? But let's think about what the inputs and what the outputs are. So the inputs, the data that ChatGPT is trained on is data from the internet. It's just huge collections of text that are found essentially in places on the internet. And on the internet, do we expect that people are writing down 2 to the 8/3 and the answer to that question? Probably not. There's probably not much reason for there to be instances of 2 to the 8/3 equals this number here. What there does exist a lot of on the internet and in the training data are math problems, right? So probably what ChatGPT is glomming onto here is this math problem where you rearrange the indices in some expression like this, and you get some nice integer. We write these math problems so that you come up with integer nice answers at the end that look complex, but end up being equal to something simple. So, this is what's happened, I think, is that the training data, the inputs here, are a bunch of math problems that turn out to give nice answers, not the real world. 2 to the 8/3 is equal to 6 point blah, 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 blah. And so you get, in terms of this problem, there's garbage that's been fed in, and so we get a garbage answer out. And so there are deep things going on here. It turns out this is a great article that you should check out. ChatGPT has done some compression here, like we do image compression for things like JPEGs, and there's lost information in that process. So we shouldn't expect this very impressive fancy black box to give us good outputs. And the reason, again, is this idea that if you feed in data that's wrong, that's not appropriate for the problem you're trying to solve, you shouldn't expect to get good outputs. So garbage in, garbage out. How can you diagnose this form of BS? Well, by looking at the inputs and the outputs and being a little bit skeptical.